So we're going to take a look at the second part of section 5.2. So we will call this part 2. In the first part, we talked about the conditions necessary for finding an inverse function. We talked about the function being 1-to-1 and how do we check that, and using the horizontal line test. And now we're going to talk about actually finding the inverse. So this is finding the inverse of the function. So let's see how we go about taking care of this. So we're going to take a look at how we find the inverse algebraically. We're going to start by replacing our function notation with y equals, and then we switch all of the x's with the letter y, and then we need to solve to get y by itself again. So let's take a look at some examples on the next slide. So in one of our earlier slides, we determined that f of x and g of x here were 1-to-1 functions. And so now we're going to take a few minutes to find the inverses of them. So in f of x, my first step is to say that y equals whatever we have. And my second step is to interchange the x and y's. Basically, wherever the x's and y's are located, I'm going to swap them. And now my goal is to solve the new equation to get y by itself. So we'll use a little bit of algebra here and get a new equation that undoes all of the work my original function did. So let's see what happens. I'm going to multiply by 5. That gives me, I need to subtract off 1. So I have to get y by itself. I now have an expression over here that gets y all by itself, and to indicate that this is my inverse, I'm going to come down here and say that using inverse notation, I have 5x minus 1 divided by -2. So let's see if my inverse undoes what my original function is telling me to do. In my first function, the original, f of x, I divided by 5. In my inverse, I'm multiplying by 5, so that makes sense. In my original function, 1 was being added. In my inverse, 1 is being subtracted. In my original function, I have a -2x that's being multiplied, kind of, well, multiplied and subtracted. So right now I'm dividing in my inverse by -2. So I might not have said this all in the correct order, but everything that occurred in the original is being undone in my inverse. Now, g of x is a little more complicated here, so I have a little bit more work to take care of, but let's see if I can likewise interchange all my x's and y's. Okay, and now I need to get y all by itself. First things first, let's get rid of the fractions. That's gone. Well, it'd be pretty easy on the left-hand side to just divide by 2 and say I have y equals. The problem is I have 1 minus y on the other side of the equation. And I'm not allowed to have a y right here in my inverse. my inverse needs to be expressed as a function of x only. So I need to continue manipulating this so I get all of my x's on one side, all of my y's on the other side. So I'm thinking I need to distribute that x. And, alright, I'm going to get an x equals, that's not my goal, I want a y equals. And now I have two places with y's appearing. So if I want to make my right hand side of the equation have just a single y, kind of looks like I need to factor. So here comes my set of parentheses, and then to get y all by itself, I can divide by everything in the parentheses. So my inverse as a function of x contains, and that would be my inverse. So on the previous slide, we were showing you how to find the inverse algebraically. If we look back at our good friend y equals x squared, you can see that this is flunking the horizontal line test. But sometimes, if we restrict the domain, we will be able to turn a non-invertible, so this has no inverse, into a function that does have an inverse. And so that's what's happening here. If we only look at half of the graph, either the positive half or the negative half, we would be able to find the inverse of this function. And now we have no trouble passing the horizontal line test, no matter where I draw my horizontal line. So what's happening here, if I apply my, here, y equals x squared, and then go find my inverse, I would have x equals y squared, and I try to get y by itself, I take the square root, but anytime you take the square root, you put a plus or a minus in front of it. And the reason that I'm having trouble on my original over here is because I have two different equations that I need to use to describe what's taking place. But on this one, I'm out of trouble because my x has to be positive. So my inverse, the positive square root of x, is perfectly legitimate since we restricted the domain. On this slide, we're taking a look at the two graphs that we had from the x squared. This was the x squared when we had the positive, and then down here, this is the square root of x that was also using the positive, and they happen to be reflected about the line y equals x, which is a characteristic of inverse functions. When you graph them, the ordered pairs that you obtain from your original function, like you know how much I love making tables of values, but bear with me here. The ordered pair 2, when you square it, gives you 4, and then 3, when you square it, gives you 9. We would find over here on my square root, if I took the ordered pair 4, we would have 2, because when you take the square root of 4, you get 2. And if you look at this, okay, make the dot a little bigger. And if I take 9, take the square root of that, you would get 3. Look at how nicely that's showing up. This is what happens when you swap, you interchange the x and y's. The ordered pairs from the x's on the original become the reverse. You've interchanged the x's and the y's in your inverse. So I'm going to leave it to you to graph the following functions, but if we want to check our answers analytically, we would need to find, well, first I need to find the inverses, and then I need to use function composition. So let's start with, actually let's start with the one with the square root in it. Okay, so y equals square root x plus 2 minus 1. First things first. And I need to go get y all by itself. So I will bring the minus 1 over, and I'm going to square both sides to get rid of my square root symbol. And then to get y by itself, I'm going to subtract off 2. I'm going to subtract off 2. Really, I'll take care of that. Okay. And then I'm going to call that, what do I have, k of x? So we'll call that k inverse of x. Now, using function composition, I need to take k of k inverse of x, and if it works, I should get plain x as my answer. I need to repeat it the other way, where I take k inverse of k of x, and I should get x that way also. So let's see what happens when I take my inverse and plug it in to the original k of x, and hope that our algebra turns out all right. So I'm going to take my x minus 1 squared minus 2, and that's going into y equals square root plus 2 minus 1. Okay, so minus 2 and plus 2, they are going to very nicely cancel. And when you take the square root of a square, the square root and the square cancel each other out. So I have x minus 1 and something's not working out here because I have a minus 1 and a minus 1. So I'm going to come back up here to check out my inverse, and I realize that back up here, that minus 1, I should have added it to the other side. So this should all be plus in here. So right here, I should have plus. And now when I look at that, I have a plus 1 and a minus 1. So I get my function composition here. To give me just x, which is exactly what I was looking for. And I hate to say it, but even if one of them works, you're supposed to check the other one to make sure that your inverses really do exist. Which means I'm supposed to check this out the other way around. So let's see if it works. I'm going to take the square root and plug it into the squared function. So let's see what happens. I need to take that square root of x plus 2 minus 1, that's going in for x, into there's x, I'm going to plus 1, and square it, minus 2. So as I look inside my brackets, actually, I can see that the minus 1 plus 1 cancels out. So I am squaring a square root, which also negates each other. So then I have x plus 2, and then that's inside my brackets, and minus 2 outside the brackets, and the plus 2 minus 2 is gone, so I have x as my result, which is exactly what I wanted to find. If you really want to have fun, you can work on the quadratic there. Don't forget about the restriction on the domain, because that's cutting the quadratic in half. And that's very important as to which positive or negative square root you choose.